Ladies and gentlemen, we are going to continue our discussion of the Aldol condensation and the Aldol reaction. And here we go. I'm on the wrong page. Sorry. I want to go back. Stop share. And share screen. And starboard. There we are. I think I was on the right place. So what we're going to do here is discuss what happens if there's more than one type of alpha H present, which is exactly the scenario here. We have these alpha H's. If you remove one of those, you get this with an anion, and I'm going to call it EA. EA is the enolate of molecule A. That's what it is. You'll notice the other one has 4 alpha H's, but because the molecule's symmetrical, we only have to talk about, any one of the possible H's. And that would give, I should have gone with a different color. This guy right here. And I'll call that EB. What's EB? The enolate of molecule B. So we're supposed to predict all the possible products here. And it tells you there's 4. Yeah, which is not usually a good reaction, is it? Any reaction that generates multiple products is not good. We're going to fix that later. So, in the question part B, it says label each product example if A reacts with the enolate of B. That's what that says. A with the enolate of B. So here's A. It will be attacked by the anion called the enolate of B. So that first product will be the one that's indicated in the question. And the exciting new bond is right here, from the enolate of B to what used to be the carbonyl of A. Oops, my mistake. There. Carbonyl of A reacted, and it's now an O, and it was an O minus, but the catalyst was regenerated and OH was made too. And then you go CH2 once, twice, and then with C with a V. So that is called the A plus EB. A plus enolate of B. Now you tell me what you think this one should be called. That's the enolate of B again. But this time it reacted with what? The enolate of B reacted with what? With B. Yeah. So that would be a normal aldol product that would result if A wasn't present. If there's no A, then you're going to get only this product, which is cool, right? We like that reaction. Let's do the other one where it's only, you'd only have one product. So leave out B. So you're going to have the enolate of A react with A. That's the aldol we did the other day. The normal, simple aldol. Enolate of A reacts with A. So I'll draw the enolate of A here on the bottom. And we won't tell it was an enolate because it lost an H and made a bond. CH2 once, twice, 3 with a V. And that is just A plus EA. These two are called simple aldol prods. Just these two. Use a gray arrow. That one and that one. And the others are called mixed. So I haven't done B plus the enolate of A, have I? No. B plus EA. So EA is the blue. I did EA just a second ago. It created that. And if it reacted with B, you're going to get OH with two ethyls. There you go. So these are mixed Aldol prods. We got this guy right here and this guy over here. Okay. But the point is, when you did the reaction with two carbonyls present, you got what's called a dog's breakfast. It's a mess. You ever have a young dog and feed it a big old bowl of kibble in the morning and his food's all over the floor all of a sudden? You know, it's a dog's breakfast. There you go. So we're going to fix that. How do you fix it? Well, if you need a simple aldol reaction, it's a simple answer. If this was your desired product, you would just treat molecule B with base, KOH, and you're done. If this was your desired product right here, you would just treat molecule A with base, and this is all you would get. Forget about a dog's breakfast. It's a nice reaction, right? But these are both equally desirable products, the ones on the outside. So we need a method that makes these reliably without having a mess. So what you do is take advantage of the fact that we're not going to use an equilibrium reaction. We're going to use an acid-base reaction that's so much favoring products over reactants that it's not equilibrium anymore. We're not going to use KOH. Remember, that was 16 goes to 20, which was kind of a good situation because we knew our enolate was surrounded by carbonyl. Here, what we're going to do is we're going to make 100% enolate in step one, and that reaction's over. It has nothing to react with yet because you haven't added it yet. So you make your enolate 100% with a very strong base, a nitrogen minus. That's much stronger, right? It's the conjugate base of an amine. So what's the pKb? Oh, I was just thinking. 14 minus 40, isn't it? Negative 26, yeah. And the most common base we like for this, it needs a new color. It's this guy right here, N minus, and it needs to have two fairly bulky groups. And the most common spectator for it is lithium. So it's called lithium diisopropyl. And here's the problem. Chemistry is very systematic, right? If chlorine needs to become an anion, how does its name change? Chloride. Here's the logic. It's good logic. Bear with me. If an amine needs to become an N minus, same logic. Amine becomes, careful how you say it. You should say amide. If you say amide, then you've got carbonyl on your brain. Amides have a carbonyl. It's one of those English words, like I'm going to polish my Polish furniture. Same spelling, it's a different word. Lithium diisopropyl amide. It's spelled amide, but really this is the conjugate base of an amine. Okay? And you're going to treat the appropriate, well, let's see, what do we want to make? We want to make A plus EB. That's this guy. So when you're done, you have to be here. So which species lost its alpha H to make this? it was B, so you started with exclusively B. That's B. And you treated it with, I guess we can just do it this way. LDA. Yes, we have to get used to the short form because it's used so commonly. LDA, that we better know what it means. Okay? LDA, lithium diisopropyl amide. And that makes this in a very high yield. There's no equilibrium here. You're going from 20 to 40, right? Wow, that's a big difference. And now you've got to give it something to react with in an aldol reaction. And I'm going to say that's going to be called B. Is that B? And my arrow should be bigger. Oh, it got black too. And you're going to have this guy right here. Yeah, we're doing one step at a time. And it's reacting with that. You're going to get an O minus. And how are you going to make that O minus into H? HCl would be a great guess. And then, what does heat do after an aldol reaction product? A plus EB. Aldol reaction product. You heat them with the same chemicals present, and you get the dehydration step. And this is the end here, everybody. You're going to have a double bond, and the carbonyl is less sterically hindered, so I want the groups always near the carbonyl. And there it is. And that's the aldol condensation product. And there you have it. End of video. A good exercise for you would be to redo this whole thing down in the bottom for the other mixed aldol product. Well, that's the one we just did. B plus, yeah. Nope, that's not the one we just did. This one. This would be your next goal, which means you would start over here with the blue one, A, and add the green one here later. And you would come up with exclusively this, proving that you don't need, you can use mixed aldol products can be made using what's called, we didn't even name it yet, directed, oh, it's already named here. Directed aldol reaction. That's this whole box. Is a directed aldol reaction. And there you have that. Good start.